computer? Yes. All right. So we're recording about comparing and contrasting. Okay, I think the recording is what's causing my feedback that I have. Interesting. Okay. All right. Can everybody still hear me? I'm working my computer.
Yes.
All right, great. Okay, thank you very much. I'm sorry about that. But so this table right here is a good way to get in your head straight the compare and the contrast between polarizability and where that you can have good nucleophiles or fair nucleophiles that are neutral as well. So we have at least 3 neutral nucleophiles on the species, but it has everything to the lone pair. And notice that this acetate right here, even though it's kind of polarizable and it has delocalization of that charge, because of its acid strength, that's what's making it a fair nucleophile compared with others. Okay, so it's really close to that of the acid strength of the HF. And so because that negative charge is not on that one atom all the time, it can wait around. It can be a fair nucleophile. So getting these kind of sets kind of in your head is going to be important for figuring out what's going to react first and fastest. Okay. So we had our nucleophilicity was based on our polarizability, it was based on our size, it was based on our charge and whether or not we have a charge or just electrons, right? Now, one of the other things that can change your nucleophilicity, especially with the halogens, is the solvent effect. If the solvent can support that anion really well, it's going to change the nucleophilicity to make it more or less of a nucleophile just by changing that solvent. So let's talk about that solvent. And we want to talk about 2 particular types of solvent. The first type of solvent is what we call a polar protic solvent. These are solvents that can hydrogen bond. Think alcohols and water and acetic acid. These all have hydrogen bondable hydrogens. We call those polar protic solvents because they have a proton they can donate. Then we have what we call aprotic solvents, and they are typically polar aprotic solvents. Aprotic solvents means they do not have a hydrogen bondable atom on the solvent. Okay, so that's the 2 big differences here. So we have a polar protic, water, alcohol, acetic acid, and then all the other solvents. And we'll talk about some of those in a moment. Now, the reason they change the nucleophilicity is because when ions start to form hydrogen bonds, they have to have those, like for example, in the case of this right here, we have water dissolving our fluoride ion, okay? And when our ions are dissolved in a protic solvent, they don't just kind of float around there. They actually start hydrogen bonding to the solvent itself, okay? So when it's hydrogen bonding and it has such a small charge, it has a strong hydrogen bond, okay? Because it has a lot of the different waters have to be there to help to support that charge because that charge is not very polarizable. It's a very small charge, and so it has to be stabilized by the solvent. However, in the case of iodine, this is big and fluffy and polarizable and further away from the nucleus. Therefore, these hydrogen bonds are weaker, okay? So because these hydrogen bonds are weaker, that's going to make it easier to have that ion leave those weak hydrogen bonds and act as a nucleophile, okay? So fluoride has to actually break hydrogen bonds to act as a nucleophile. So in the case of protic solvents, the larger, fluffier ions actually are more nucleophilic, okay? Even though the fluoride ion is the more basic. Okay, so let's talk that a little bit more, a little bit through, okay? So let's think about our polar and protic solvents here again. And so in the case of smaller non-polarizable ions, okay, we have to have hydrogen bonds to support that charge. And when we have those hydrogen bonds to support that charge, they actually have to be carried along. Those solvent molecules have to be carried along with that ion, because it can't just be a free ion because it's not very polarizable. And therefore, it actually looks like a much bigger, much more sterically hindered ion than if it were something that had weaker hydrogen bonds. Okay. So what this means is that in a protic solvent like water, alcohol, and acetic acid, iodine is much more nucleophilic than bromide. Bromide is much more nucleophilic than chloride, and fluoride has the strongest hydrogen bonds to the solvent, and therefore it is the least, it's the least nucleophilic of the set. Okay, so this entire thing runs because of the hydrogen bonds. So if we had it in a different solvent that didn't hydrogen bond, we might change the nucleophilicity of that series. Okay. So let's talk about what these different solvents are. And like I said before, protic solvents are things that have hydrogens that can hydrogen bond. And I've mentioned all these already. Okay, but now let's talk about polar solvents. And we have to have polar solvents because they have to support, either through dipole or something, they have to support those ions. So we typically use polar solvents, and we're using aprotic solvents, meaning solvents that don't have hydrogen bonds. And some of the typical ones we use are this right here, dimethyl formamide. So it's just formic acid with a dimethylamine. Dimethyl sulfoxide, or DMSO. Notice none of those are acidic hydrogens. Acetonitrile, right here. We don't use hexamethylphosphoramide much anymore because it's quite bad on the liver. But acetone, nice, cheap, simple solvent. It's a non-protic solvent. Diethyl ether, not as good, but some of the bigger ions can dissolve in diethyl ether. And then THF, tetrahydrofuran. We're going to use that solvent a lot, especially these two solvents here when we get into Grignards and stuff. These are really common solvents in that system. Okay, so these are the aprotic solvents. Okay, now in general, the non-polar solvents don't have are not able to dissolve up the reagents, and so we rarely see them used in this system. So we typically divide all of our SN2 and SN1 reactions into a polar protic solvent or a polar aprotic solvent. Okay, so now that we know what the difference is between our polar protic solvents and our polar A solvent, we can see that we can change the nucleophilicity of different species based on which solvent we use. Okay, so nucleophilicity increases down the column on the periodic table. And so the opposite trend is predicted by the basicity of the nucleophile when we go across the table. Okay, so we need to think about polarizability of that nucleophile. The further away those electrons are from the center, the more polarizable it is, and therefore the more that it can be stabilized in that system. So let's take a look at this nice little system. We have something big and polarizable, and it has a negative charge on it here, and we're displacing it here. So we're not looking at sterics. All we're looking at is the nucleophilicity of the charged sulfur species. Okay. So when we look at that and we put it into a polar protic solvent, okay, what we're going to see is that we're going to have the electrons. Let me use, I guess I'll use right here. The electrons on the sulfur atom here that are forming that are going to be sharing that negative charge with as many hydrogens as possible to be able to stabilize that charge. Okay. And then the sodium ion that was attached to it is going to dissociate, and it's going to be stabilized by the lone pairs on the oxygen. So that's how this molecule is going to dissociate in water. Okay. And so in general, when we do this, it decreases the nucleophilicity of the molecule because we have so many of these water molecules hydrogen bonding around it. So if instead of using water as our solvent on this side, right here, Let's use acetone on this side over here. In acetone, we don't have hydrogen bond because it does not have acidic proton. However, it does have a dipole moment, right? So we have the partially positive side here and the negative side here. And so what happens is we have an ion dipole interaction, which is not as strong as the ion hydrogen bond interaction, okay? Meaning that more of the charge is still on the sulfur, and that should increase the nucleophilicity of that anion. And notice that the counterbalancing sodium here is being counterbalanced by the electronegative side of this system through that same dipole ion interaction. Okay, so in this case, water is inhibiting us. Those polar solvents are inhibiting the nucleophilicity of the reaction, but the non-protic polar systems make it more reactive. Okay. So this is true until we have the halogens, okay? So when we solvate the halogens in protic solvents, we actually, the solvated nucleophile makes them less reactive. The larger nucleophilic atoms that are polarizable decrease the activation and energy of that transition state, and therefore the less solvated, freer molecules move through the solvent more than the smaller polarized ions. So what does this mean? In our system here, in polar protic solvents, our iodine is more nucleophilic than our bromine, than our chlorine, than our iodine. In polar protic solvents, the basicity does not follow nucleophilicity. Okay. So, but if we put them in polar aprotic solvents, we reverse that trend. In polar aprotic solvents, fluorine becomes the more electroactive, the more nucleophilic species, and iodine becomes the less nucleophilic species. Okay. So that's one of the most interesting things about at least the halogens in general in the polar aprotic systems, is that fluorine now becomes the more nucleophilic of the system. So let's say you wanted to use fluorine as a nucleophile. You would want to choose your solvent such that it didn't have a hydrogen bondable species. And so we would want to see things like, if you wanted to displace something with fluoride, you want to use acetone or THF in your reaction. But if you wanted to use iodine to displace something, you'd want to use water or alcohol to be able to displace that. So we want to look at that solvent effect as it affects the nucleophilicity of the halogens in particular. In other systems, it just changes the nucleophilicity slightly, but in the halogens, it completely flips the order. Okay, so in polar protic solvents, iodine's best. In aprotic solvents, fluorine's best, and they're completely opposite. Okay. So this is going to review everything we know about SN2 reactions up to now. And then I have the part 3 that we'll talk about as well. So SN2 reactions are by nature bimolecular reactions. That's what the 2 means. They're nucleophilic because we have a nucleophile, and we have substitution. Okay. So we always involve a nucleophile and an electrophile, and we can equate nucleophile and electrophile to Lewis acid, Lewis base, right? Our nucleophile is going to be our Lewis base because it has the electrons to share. Our electrophile is equated to our Lewis acid because it wants to be shared, it wants to grab those electrons. Okay. The rates of the reactions depend on several things. One, is the leaving group a good group? Okay. Excuse me. The weaker the base, the better the leaving group. So the stronger the conjugate acid, the better the leaving group. For example, iodine is a great leaving group because it has a very strong conjugate acid and makes it a very weak base. The next thing that affects that is sterics, okay? So if we have a small anion that we can have come in and weave through all the different solvents and attack your nucleophile, those are good nucleophiles. We think small things like the halogens and methanol, the salt of methanol. However, once our nucleophile gets really big and bulky, it starts getting harder and harder to act as a nucleophile because it's getting a smaller and smaller way for it to come in and do that substitution reaction. So anything that has like a T-butyl group on it or a couple of benzenes hanging off it, it's going to be very difficult to act as a nucleophile. Okay. Things that are not very polarizable, weak polarizable bases, things that are polarizable are good nucleophiles because they can start to stretch that electron cloud and start to form that bond early. Things that are less polarizable are poorer nucleophiles. So for example, our neutral species, because we don't already have that lone pair free and clear as a charge, we just have to rely on lone pairs on a system. And then our solvent effects, okay? Polar aprotic solvents will speed up the reaction. Polar protic solvents will allow hydrogen bonding and actually will slow the nucleophile down and or make it less nucleophilic. And remember, in addition to that, in polar aprotic solvents, fluorine is the more reactive nucleophile. In polar protic solvents, iodine is the more active nucleophile within the set of halogens. Okay. Nucleophilic substitutions can be reversible if we're looking at our kinetics versus their thermodynamics. And what we're really looking for is in the product of the reaction, what is the stronger base? In this case here, we have the the iodine ion here versus the chloride ion here, okay? So if we think about it, this chloride is actually the stronger base because it's the weaker acid, and therefore it's shifted in this direction, okay? But there is an opportunity for it to go back. In this particular case, because the lithium iodine is in solution, there is a little bit of backflow in that reaction, and we end up with our thermodynamic product. Okay, our product that has the weakest base at the terminus. Okay, at the end of the reaction. However, if we change our solvent, we can actually get that to go back. Okay, so if we change it such that our material actually precipitates out of solution, such that our chloride ion, even though it's the stronger nucleophile, it's the stronger base in this particular thing, if it comes out of the reaction, we can actually end up forming the kinetic product, which is the one with the iodine on it right here. And this is one of those weird, odd reactions called the Finkelstein reaction that it took them a long time to figure out why this worked. And the reason it works is that even though the chloride is the weaker, it is the base, the better base here, the fact that it is no longer participating in the reaction means that you can drive your products to the kinetic product and not the thermodynamic product. However, in most cases, when we do these things, we see that it is mostly shifted to products. There might be a little bit of reversible, but we just might not see it. Okay, and then of course, our sterics have an effect on our reaction rate. Our methyl groups with a leaving group on it are our fastest because we don't have any sterics to inhibit them. Our attack by our nucleophile can be, in a bunch of different directions here because you have less of electron-electron repulsion driving it away. However, by putting just one on here, we decrease the rate by 145%. And that's because sterics now. We have fewer places for our nucleophile to come in. And again, if we add another substitution, it slows it down even further. almost 7,000 times right there. And then by the time we get to that tertiary alkyl halide, you almost don't measure any product at all. So it would be very difficult to compare results. So structure of the substrate greatly affects the rate of the reaction. Okay. And this has everything to do with having a bigger or harder to make transition state. If you have less electron repulsion, it makes your transition state less of an energy barrier. So the smaller the nucleophile, the lower our activation energy is. The lower our activation energy is, the faster our reaction goes. Okay. In the case of something big and bulky, we have so much electron repulsion here that we have to force more energy into the system. We have to add a greater activation energy just to get it to even start forming that transition state where we're starting to form a bond and starting to break the bond. And so if we look at sterics as a function of electron repulsion, we need a lot more energy to get into the system to make it go. And so the sterics are driven by energy. And we can see it in that activation energy in the coordinate diagrams. Okay. So one of the other things that happens here is that we also have to think about sterics not just on the carbon itself, but sterics on the carbon next to it. Okay. So one of the things we hadn't actually talked about up to now is that we have a primary, we only have one methyl group here. And it has, so we have, this is just ethyl bromide here. And we have a relative reaction rate of having our nucleophile come in and attack it of 1. Okay. So if we add another carbon to this, okay, so that makes it slightly, this whole group right here has just doubled in size right here. And that's going to decrease the rate by about 20%. So by taking that, doubling the size and adding another third here, it decreases it again. And by the time you get 3 of these methyl groups on here, even though we still have a primary alkyl halide, the fact that you have a big group on that primary alkyl halide slows the reaction again. So this is our primary steric hindrance, is what's attached to the carbon with the leaving group. But this is a secondary steric hindrance on what's attached to our primary carbon in this case, that is making it still bigger and bulkier. Okay, so that is all the SN1, SN2 reactions that we're going to do on these sp3 hybridized carbons. Okay. However, there's a couple special cases of sp3 hybridized carbons that change the reaction rate a little bit. Okay. And what we call those is the benzylic, allylic, and phenolic. So in the case of things like this right here, we have sp2 hybridized carbons right here. Those do not undergo SN2 reactions. Okay. They undergo other reactions, but not SN2 reactions, because they do not have an sp3 hybridized carbon. However, we can have a vinyl group 1 over or a benzene 1 over from an sp3, and those still react, okay? And those actually tend to react faster because we have that adjacent pi bond to help stabilize the transition state. We have extra electrons as it's going through that transition state. The pi bond here can help stabilize that transition state. So what we see here is, in the case of our methyl primary and secondary, we see the same trend of relative reactivity we have, and that's based on sterics. Okay. However, once we get to that 1 over carbon with having that double bond, we can actually speed up the reaction rate because our electrons can donate to that transition state and stabilize it. But notice those sp2 hybridized carbons don't react at all. Okay, so that's another special case where we have things that can react even faster than all methyl groups because of electron donation by a double bond nearby, but not directly on the carbon that we're doing our substitution on. Okay. And that has everything to do with remember in our transition state here, we're moving our sp3 hybridized tetrahedral carbon into a trigonal planar carbon. When it's in that trigonal planar carbon, those pi clouds can help stabilize it. Those pi's next to that now trigonal planar transition state stabilizes it. And we're going to talk a lot about that stabilization of that state when we talk about carbocations in elimination reactions. So, but just keep in mind that the reason it's working is because we are going through this trigonal planar transition state, and then those p orbitals can actually help stabilize that charge. But these cannot undergo that because we have the sp2 hybridization means you have an available p. You cannot do SN2 reactions on anything other than sp3 hybridized carbons, and that's what that's. Okay, the last thing I want to talk about with SN2 reactions is the thing that's kind of hard, is that what if you make a nucleophile on the same molecule that you have a leaving group on? Okay, so this means that you have a nucleophile in close proximity to a substitutable carbon, right? And as soon as you deprotonate, in this case, we're deprotonating a carboxylic acid. This is our leaving group over here, our chloride here. And when we deprote that, we turn it into a nucleophile. Okay. Acetate is just a fair nucleophile, but it's a nucleophile. So when we deprotonate that, we have an opportunity here, right? We've now made a nucleophile, and we now have on that same thing a leaving group. So what can happen is you can actually have that nucleophile drift around in solution and attack another molecule, okay? Or, so that would be an intermolecular reaction where we're doing between two molecules here. Or it can go ahead and somehow, using its free rotation, go around and displace the one on itself. Okay. Which one's more favorable? Okay, the having your nucleophile waiting around until it wanders around and finds another molecule, or the fact that it's already just going to be randomly rotating and flopping around. It actually has enough of this energy. It's in close proximity, and it will close rings very rapidly in the system. So in our SN2 reactions, one of the things that really speeds up this reaction is to have an intramolecular SN2 reaction, which forms rings. So basically you have the nucleophile and the leaving group on the same chain, and then it forms rings. Now, this is true for making things like 5, 6, and 7-membered rings, 5 and 6 being the most thermodynamically favored. Okay, questions about just the generalized system of the SN2 reaction? Okay. So I have another set, which is 6.3, that I'll start to pull up here while you're thinking about your questions. That's 6.3, yeah, there we go. And we're gonna start to introduce the next topic, which is the opposite of SN2 reactions, which is an SN1 reaction, where we have a unimolecular substitution reaction. Okay, so the primary way an SN1 reaction is different than an SN2 reaction is the fact that you typically have your leaving group leave first, okay, creating a transition state. Okay, because of that, we only care about the concentration of our substrate. Remember, our substrate is the one that has the leaving group on it. Our substrate is the one that's going to have the substitution reaction happen to it. Okay, so In the case of SN1 reactions, because it only depends on the rate of the, it only depends on the concentration of our substrate, we call it a first order reaction. There's only a 1 up here. And so if we double the concentration of our substrate, it'll increase the rate. It'll double the rate of the reaction. If you increase the rate of the nucleophile, increase the concentration of the nucleophile, it doesn't affect the reaction at all. Okay, that's how we can actually measure whether something's undergoing an SN1 or an SN2 by just taking the same concentration and changing the concentrations of the different substrates. We can see it either increase, decrease, or stay the same. Okay. So if it doesn't rely on the concentration of our nucleophile, it must be unimolecular, meaning it must depend on itself alone. So how do we know? Can we make this happen? Okay, so the way we do this is we actually end up having our bond break first with our leading group, okay? Because the concentration of our nucleophiles is not important, we must break our bond first. And so that was one of those mechanistic things we talked about that can happen. We can break bond, we can do it homolytically or heterolytically. In this case, we're going to do a heterolytic bond cleavage where the electrons are leaving with our leaving group. And in the process, we are generating a cation. Okay, so if these two electrons are leaving with the leaving group, we're creating a cation. Okay, so we're creating a carbocation. Okay, and the key phrase about a carbocation is we have a trigonal planar sp2 hybridized carbon with an empty p orbital. Okay, that empty p orbital is where the positive charge resides. Okay, so this is the important part of an SN1 reaction. We have this trigonal planar structure with the empty p orbital above and below the plane of that carbon. That has an impact on what our products are going to look like. Now, at this point, our nucleophile can come in and either attack the top or the bottom of this to give our final product. Okay. So what does this mean? Okay, it means that in any typical reaction, we'll end up having our leaving group leave first, formation of a carbocation, and then attack by our nucleophile last. Now, one of the interesting things about the SN1 reaction is we can use very weak nucleophiles because we're already forming this highly energetic transition state, this intermediate. We're forming this highly energetic intermediate so that we can use very poor nucleophiles to come in and react with systems. Okay, so let's look at the reaction diagram associated with that. So the first step in our reaction diagram is we have to have enough energy to break that bond first, okay? So our transition state is not the making and breaking of a bond at the same time, it's actually just the breaking of this bond. And in the breaking of that bond, we start to polarize it right there, and then we have enough heat that it completely breaks apart, giving us our intermediate. And the thing here in this part here is our intermediate. And notice it's a trigonal planar carbocation, and that we can then, at that point, have our nucleophile come in and start associating with either the top half of this empty p orbital or the bottom half of this empty p orbital. Okay, so it can attack either side, and in this case, we can use just lone pairs. It doesn't have to be a charged species. Okay, once we do that, we hit an activation energy where we are starting to form that bond. It's starting to associate those lone pairs from the oxygen. They're starting to reach out and grab at that positively charged carbon. And then once we do that, we actually cascade down to our next intermediate. In this case here, it's our protonated charged species. Okay, so we formed our sigma bond. This is our new sigma bond. However, our oxygen now is electron deficient and has a positive charge on it because it would prefer to have that lone pair back. Okay, so at this point, we have to have something come off and pull a hydrogen off to act as a base. And when we do that, that's that next energy transition, getting this base to come in here and start to pull that hydrogen off, is this last activation energy. And once this leaves, we end up with our neutral molecule at the end. And that neutral molecule is our product. Okay. So now, this is if you're coming in with a neutral nucleophile to attack your carbocation. If you came in with a charged nucleophile, you end up with only a single transition state and 2 activation energies in your system. But this is the most complicated part of a coordinate diagram for an SN1 reaction. Okay, so what I'm going to do is I'm going to go ahead and go over the mechanism one more time here, and then we're going to break for the weekend here. Okay, so the overall reaction is we typically have something that has a substituted carbon that has some kind of leaving group, some kind of polarizable bond where we have something that will leave and form a nice stable ion. Okay, and in that transition state, we have this heterolytic cleavage of a sigma bond to give us a positively charged carbon species and a negatively charged leaving group. When we go from the sp3 hybridized carbon to this intermediate, we now have an sp2 hybridized carbon with an empty p orbital above and below that plane. Okay. Then at that point, we can have a nucleophile come in and attack either side to generate our new sigma bond and reconvert our sp2 carbon back into an sp3 carbon. Okay, so there's a hybridization change in this mechanism. Notice there wasn't really that. We had that transition state where bond was making and breaking at the same time. So it was never really lost its sp3 hybridization. In the case of the SN1, we do lose that hybridization. Okay, so then the last step is coming in and attacking that species. And in this case, we do have the attack of a neutral species, meaning that when we're starting to form this transition state, these electrons are starting to get into that empty orbital and starting to form a new bond and changing the hybridization back to that sp3 until we form our new sigma bond. But because we attacked from the neutral species, we had a positive charge and a neutral charge. We now have a positively charged intermediate right here. And then we have to wait for something to come and pull that proton away, something to act as a base and give us our electrons back to our oxygen. The hydrogen is transferred to the base using the base's electrons to give us our neutral final product. All right, so questions on the basics of the SN1 mechanism. Excuse me. Okay, so what I'm going to do is I'm going to stop here. What we're going to do is we're going to pick up on this SN1, SN2, and by the end of this chapter, we're going to compare SN1 and SN2, and we're going to see that sterics, leaving group, and solvent are directly related to, and the nature of the nucleophile, whether it's a base or just a nucleophile, is going to compare and contrast which is going to be favored for SN1, which is going to be favored for SN2. Okay? So if you want to hang out and ask a question, go ahead. If you not, I'll go ahead and stop recording.